Hi, everybody. This is Dr. B, and let's go over the Grignard reaction, both in theory and in practice. We will cover the reaction and the reagent, which are two different things. First, we'll prepare the reagent, the alkyl magnesium halide, or in this case, the aryl magnesium halide, and then we'll use it in the Grignard reaction. We'll go over the mechanism for the reaction, how incredibly useful it is, what can go wrong, which is a lot, the procedure we use, and why we're doing the steps we're doing, and your fake data that you'll use to make a lab report. And then finally, we'll show you the scoring guide. So let's dive in. Okay, so the reaction involves taking an alkyl magnesium halide to react it with a carbonyl compound and form typically new carbon-carbon compounds that contain an OH group. So this reagent is generated from an alkyl halide. The magnesium slips in. We'll tell you about that more. And then it's now a nucleophile, and it'll react with things that are electron deficient, most notably carbonyl compounds, but not always. And in the end, generally speaking, some sort of an alcohol and a magnesium salt, which you get rid of. The reagent, in this case, is your aryl halide, which gets converted into phenyl magnesium bromide. This is really kind of cool because the Germans call this Umpolung, Umpolung, which means a reversal. Because right now, bromine is pulling electrons away by virtue of its electronegativity. And so this site here is positive. It's your electrophile. And this part here is electron rich. That's your nucleophile. But magnesium is capable of slipping in. This was discovered in the early 20th century by Victor Grignard, for which he got the Nobel Prize. And in presence of a scrupulously anhydrous solvent that is oxygen-free, which is a pain, you can make this aryl magnesium bromide. Do note that a couple of companies, including the Aldrich Chemical Company, do manage to sell this, though a lot of scientists won't buy it because it's so sensitive. It's better off being freshly prepared. So that's phenyl magnesium bromide. Here's the mechanism. You start with your alkyl halide, you add magnesium, and there's an electron transfer. Magnesium likes to lose electrons, and specifically two of them. But in this case, it has been ascertained that it initially loses one. That's called a radical cation, and that's a radical anion. So it switches an electron from magnesium to the alkyl halide. At that point, it splits homolytically, meaning that those two electrons split right down the middle there to give you a very active free radical as well as an anion. Usually they can get strong evidence that this is preceding by these very rare free radical processes by adding something that will suck up free radicals, like vitamin E, for example. And if the reaction is halted by that, it's very likely it's going by a free radical process, and this one is. Once you have that free radical, it's very reactive. It'll react with that radical cation that we generated right up there to form the carbon to magnesium bond, but you still have your positive charge. Free radicals are very reactive, but not charged. And at that point, that will pick up the halide that's kicking around, and lo and behold, it has slipped in by a much more complicated mechanism than you might have imagined. But once you've got that thing, wow, you can do so much with it because you've got a carbon with a negative charge, and so you can react it with any sort of electrophile. Most common, carbonyl compounds. Have a look as you go around the horn. They're almost all carbonyl containing compounds. We'll show you a couple in the end that aren't. Two things. One, incredibly useful reaction, and number two, there's a zillion me-too substances, RZNX, RNIX, all sorts of similar ones that have spawned as a result of this initial discovery. It's a great way to make carbon-carbon bonds. The mechanism of the reaction once you've generated the reagent is that it will react with any kind of electrophile. And while carbon dioxide is a great one, electrons pulling away on both sides, you can also draw resonance structures that really show that this carbon is electropositive. And what is that? That's just dry ice. So we're going to make phenyl magnesium bromide and throw in some dry ice. We have to be careful because dry ice can have water come all around it. It pulls water, so we have to make sure it's water free. And once you do that, it'll attack that. It will form the carboxylate anion, right? So imagine this negative charge. I'd rather that line was a little closer to carbon, but imagine that carbanion attacking that carbonyl carbon and then kicking out those two electrons to form an alkoxide. And you do have the MgBr plus at that point, so it'll form that substance, and it needs to be quenched, meaning add an acid, and then you'll get your free carboxylic acid and your magnesium salts, and you're good to go. In our reaction, like anytime you generate a carboxylic acid, if there's other things in there, it's a great idea to add base so it goes into the water layer. Wash out anything that is not in the water layer, and then reacidify, and it'll get rid of everything essentially except the carboxylic acid. And we do that. Now, what can go wrong? Oh God, all sorts of things. If you have magnesium oxide on the surface of your magnesium, you're not going to get a reaction. It requires pure magnesium metal, not magnesium oxide. Solution, well, sand down the surface just before you add it so that you get rid of that oxide. That works pretty well. It also increases the surface area if you make it all rough on the surface. Store the magnesium under an inert gas so it can't form the magnesium oxide to begin with. For some reason, scientists almost never do this. They really should, but it's a pain. Or you could just throw it in and then scratch it inside there to expose some fresh surface that cannot possibly oxidize because it's got a solvent in there. So that's the most common method. Once you generate your reagent, it can still react with water because this is minus. Water has H plus in it, a little bit, right? And so this can turn an alkyl halide, don't forget this started with an alkyl halide, into an alkane. Solution to that problem? Well, maybe it's not a problem at all if you want to turn an alkyl halide into an alkane. It's a nice way to reduce it off. Another way to do it is just make sure there's no water present. Now, in New England or in a moist environment, that's hard to do. Most people oven dry their glassware in the old days, and I go back to the old days. We used to flame dry our glassware. Super dangerous, and I've got the war stories to prove it. So oven drying it is a much better way to go. But if you do that, beware. When you pull your glassware out of the oven, what's it going to do? It's going to suck in air as it cools. And if that air is wet, you haven't accomplished anything. So as soon as you take it out, you either need to put in an inert gas or just put in some kind of drying tubes. And you let air come in, but it has to run through, say, a calcium chloride in a tube, and that'll keep it dry on the inside. Another thing that can go wrong is it reacts with oxygen to form peroxides. That's not great, and that's a side reaction. How do you solve that? Use an inert gas. Most undergraduate labs don't bother with that due to the expense and the difficulty of everybody working in a hood. So if you use a low boiling solvent, that also generally works well because there's enough partial pressure of that solvent that it just has a bed of, say, diethyl ether, which is also inert under the reaction conditions. So it's kind of a low-tech solution that way. Finally, that alkyl halide can react with the alkyl magnesium bromide, can't it? Because this is electropositive there. This is electronegative there. So this can react with that. Solution, add this stuff slowly so it forms that, but you don't have excess of that coming in. I think inevitably there's almost no way to prevent this completely, this Wirtz coupling, but if you add it slowly, you can help minimize it. The procedure we'll be using is to take your clean and dry your reaction tube. We'll oven dry it briefly. We'll include a pressure vent so that when things are going on, this doesn't pop off. We'll prepare some bromobenzene in ether. There's your amounts. 0.33 grams of bromobenzene. That'll be our limiting reactant. Because we'll use an excess of magnesium, we'll throw it in there. Right now it's just in the ether, right? We want to minimize the Wirtz coupling. And then we will add the bromobenzene slowly. And if we're lucky, it'll initiate the reaction after you add just a little bit. If you need to, we'll scratch it. And after that, we'll then let her go, and it will reflux boil. The magnesium gets consumed just about, because we're using just about one equivalent of it, and you'll end up with your phenyl magnesium bromide in ether. At that point, all we got to do is throw it in dry ice, right? Dry ice is our electrophile, so we use an excess of crushed ice, not the kind that is all wet on the surface. We want it to be dry, water-free. So we keep the everything covered to try to keep it from getting water all over it. We throw it in, and it'll generate the magnesium salt of the benzoic acid, and then we have to quench it with HCl to go from that substance to that substance there. Then we do a base wash. Now, I'm not showing it here, but we'll wash it with base. When you add base, this forms a water-soluble salt. You add a solvent to remove anything which can't form a salt. Hint, the Wirtz coupling product, every byproduct basically cannot form a salt. And so when you reacidify this, you've nicely separated out all those side reactions. But if you get a lousy yield, it's probably because a lot of those things occurred. So here's your observations. We didn't get an observable reaction after the addition of all of the bromobenzene. Scratching it with a glass rod did initiate the reaction nicely. Boiling was observed. All the magnesium got formed. Wonderful. However, there's probably something slightly wrong here. I don't know if they added the bromobenzene slowly because things didn't kick in until all of it was there. The textbook procedure was followed throughout, including the base wash, and we get 0.3 grams of a product that was isolated as a fine white powder. Important to don't forget that the final workup did include a base wash. Here is the scoring guide. It's a little fuzzy, but I hope you can see it. And I hope that helps everybody. Send me any questions you have. That is the procedure for the Grignard reaction.